Okay, in this lecture, we're going to talk about interference, which for those of you who took 151, we've talked about wave interference before, but we're going to add to it something called Huygens principle and talk about how fundamental interference is to the way that waves, light waves in particular, but really all waves behave. So just a little review about superposition and interference. When we have two waves that overlap, we sum their amplitudes. Okay, so you can see that in a lake like this, where you might have, say, the wind creating one wave and a boat going by that creates another wave, and maybe a wave bouncing off the shore that creates a third wave. When you try to figure out what the wave is at any individual moment in any individual spot, you're going to add those waves together. This is called superposition, and it creates a more complex wave generally than the initial wave. We can either have constructive interference, where we add the resulting wave and we get a higher amplitude, or we can have destructive interference, in which we end up with a lower amplitude. So if we look at this wave here, wave 1 interferes with wave 2. We superimpose them, we add them together, and you can see that, say, at this point, we're getting constructive interference. My amplitude here is positive, here it's positive, and so my amplitude of the resulting wave is larger. So right here, we have a nice example of constructive interference. While right here, we have an example of destructive interference. I have a positive amplitude here, I have a negative amplitude here, and the result is that I have an amplitude of my resulting wave which is smaller than this big wave, right? So it's constructive here, it's destructive here, and you can see how we're adding these two together, right? I take a nice smooth wave like this, add a wiggle to it, and this is what I get. This is my complex resulting wave. So that's superposition, constructive interference, in which our amplitude gets bigger, or destructive interference, where our amplitude gets smaller. All right, so now we're going to add something to this idea of interference, and that is the idea of phase. And the phase of a wave, and phase means essentially at a given time, where is the wave in its up and down oscillation, okay? And usually we talk about two waves either being in phase or out of phase. If they're going up at the same time and down at the same time, we call that being in phase. This plays a large part in whether interference is constructive or destructive, especially when we're talking about waves that have the same frequency or wavelength. So in both of these images below, the two waves that we're adding have the same frequency as each other, right? Here we can see we have one wavelength that's this long, our wavelength is this long. Over here, again, our wavelengths are the same, and we assume they're traveling in the same medium, so their frequencies are the same. But the result of their interference is drastically different. In the left image, our waves are in phase, right? So when we add here, we get a much larger amplitude. When we add here, we get a much larger amplitude. Two positives added together, a big positive. Two negatives added together, a big negative. Here on the right side, though, the waves are exactly out of phase, and the result is destructive interference. A positive added to a negative equals 0. 0 added to 0 equals 0. Negative added to a positive equals 0. And so our resulting wave has no amplitude at all because these are perfectly destructive waves. They're exactly out of phase and they're the same frequency, and so they essentially destroy each other. Okay. So when we talk about the behavior of electromagnetic waves, and really any kind of waves, it's important to recognize how interference and phase work here. So remember that a wave is a disturbance traveling through space. At each point it travels, an EM wave creates a disturbance, that is, that oscillation of the electric and magnetic fields. Okay. Each recreation of the disturbance creates a new wave, right? As my wave goes up here, it changes the magnetic fields and creates an electric field that changes. That changing electric field then creates an electric field and a new magnetic field. That new magnetic field creates a new, it goes on forever and ever, right? So at each point, we get a new wave that creates and spreads out in a circular direction from our disturbance. Now, why don't we see that, right? Why don't we see what we call wavelets here? It's because of interference, right? At these points in the middle, if I get a little wavelet that's created at time naught, at my initial time period, they're going to spread out, and at, say, this point, I'm going to get some of them that are uh, the amplitude is positive, some that it's negative, some that it's zero, and essentially they're going to cancel each other out in that middle area. At the wave front, though, because of the geometry of this, we actually get those wavelets constructively interfering with each other. So we have these little wavelets forming, but most of it gets washed out except at the wave front. And so to us, it looks like that wave is just one wave moving forward. But it's actually all these little tiny waves that are running into each other and either constructively or destructively interfering. This idea is called Huygens principle, okay? And it's true of all kinds of waves. Okay, it's particularly important when we deal with electromagnetic waves, but it's not just electromagnetic waves that follow Huygens' principle. This principle actually is a nice way to go kind of step back and understand what's happening when we talk about refraction. So when we remember, refraction is when it looks like light is bending as it goes into a new material. How does this principle help us understand that? Well, let's look at our images here. If we think of each color here representing a moment in time, I've got a nice little blue wavefront here, and the dots are nothing except just the centers of my little wavelets that are going to form. So my wave here is moving along in the downward direction. At moment 0, it's blue. A moment later, my wavefront is this green dotted line. But what Huygens' principle tells us is it's not really just that green dotted line. It's all of these green wavelets that were created by my blue dots here. Okay? They destructively interfere in here, but they constructively interfere along right here. Okay? We can see the same thing happening down here at the next step, right? At my yellow spot, I have these big circles, which are still the waves created by my blue dots, but they've spread out more because it's one time step later. My little yellow wavelets here are created at my blue dots, and they spread out. And here you can see that constructive interference even better, right? My wavelets created 2 time steps ago match up with the wavelets created 1 time step ago, and that's how that constructive interference happens. So now my wavefront is this nice dotted line at yellow. Okay, everywhere else other than the wavefront, those wavelets are canceling out. But now we see danger ahead, right? We're going to move into this new material, and this new material has index of refraction of 2. So the speed of propagation is going to slow down. The waves are going to have the same frequency, but their wavelengths are going to be half as big as they move through that new material. So what happens? Well, at time step 3, which is brown here, you can see that the disturbance at this yellow dot, which is the same yellow dot we have here, has spread out like this. And notice that its circle is smaller than these wavelets up here. Why? Because this is what index of refraction means. This material, light travels 2 times slower through here. Okay, so in the same time step that the wavelet created this circle in my material up here, down here it creates a much smaller circle. Okay, the next time step at purple, over here I continue to move the same distance in that time step. But after 2 time steps, the brown dot here has created this wavelet, right? A smaller wavelet. This yellow dot now has been in the new material for 2 time steps, and so it creates this new wavelet here. And then the same thing happens for the aqua time step. Notice what happens to our wave front here. Where are we constructively interfering? Now our constructive interference is along here. Okay, this is where our waves, little wavelets, are matching up and adding to each other. So now, instead of having this nice horizontal wavefront moving down, it appears that the wavefront has bent, right? What's happening is that our constructive interference has changed and sent that in a different direction. Okay, so that's why refraction happens, and that's how Huygens' principle can help us understand what's going on in refraction. There are also some really crazy explanations of this that talk about quantum mechanics. This is in some ways simplified, but it is interesting. I think it's a really useful way to see refraction.